So hopefully everybody had a great fall break for this virtual lecture opposed to regular lecture. I'm going to be working off of one screen. I will be going in between PowerPoint and OneNote, still taking notes on OneNote, but it'll be one screen instead of two. All right, so last time we met, we were talking about how cells take advantage of a solute gradient across a membrane. The one that we were most interested in were sodium ions and potassium ions. As you are aware, this differential gets established by the sodium-potassium ATPase that uses a lot of energy in your cells. And when we last met, we were looking at how sodium ions and potassium ions would behave if they were given the opportunity to flow across the membrane towards their electrochemical gradient. And it was very clear that sodium ions would flow in because they're positively charged and therefore they want to neutralize the negative charge inside. And also they would flow in because the concentration is higher on the outside than it is on the inside. And then we looked at potassium ions, and it was a little bit difficult for us to determine which way they would flow because based on charge, they would still want to flow in, but based on concentration, they would flow out. In the next lecture series that will also be available virtually, we'll talk about how you can calculate that. But I told you for the time being, believe me when I tell you that sodium or potassium ions will be flowing out. We also defined that there's a resting membrane potential for the cells that we're interested in studying. It's going to be 70 millivolts more negative on the inside than the outside. So we say it has a resting membrane potential of minus 70 millivolts. And then we also defined equilibrium potential. Equilibrium potential is what the resting membrane potential would be if we gave a particular ion, say for instance sodium ions, the ability to go to equilibrium. So if the sodium ion went to equilibrium, the resting membrane potential would change from minus 70 millivolts to plus 55. That's because you have this massive rush of sodium ions that are positively charged that would go into the cell, and that would result in a membrane potential of plus 55 if sodium ions were at equilibrium. Similarly, we looked at what would happen if potassium ions reached their electrochemical equilibrium, and that was a negative value of minus 90 millivolts, which was very close to the resting membrane potential. And we kind of concluded before we left on Friday before fall break, where I told you that there's a calcium leak channel that sets the membrane potential at minus 70. So a little bit of a potassium leak channel that sets the resting membrane potential at minus 70. So there's a little bit of potassium ions that will leak out over time, and that is how we get to a membrane potential that's very close to the equilibrium potential of potassium ions. And so just kind of shifting over to OneNote, I want to go through and just redefine what we have in a cell when we're thinking about generating an action potential, and that's what we're going to look at today. And it's certainly going to depend on the disequilibrium of those two ions. It's also going to depend on a couple of channels. So the first is going to be voltage-gated channels. And to be specific, voltage-gated ion channels. So these are still channels. The ions that we're going to look at are still going to flow through them in a passive process down their concentration gradient. But the key term here is that they're voltage gated. And we'll talk a little bit about that. But for now, what it means is that they're going to open and close based on the membrane potential or voltage. All right, the two that we're interested in looking at are going to be voltage-gated ion channels for sodium and, no surprise, voltage-gated ion channels for potassium ions. Both of these voltage-gated ion channels are going to be closed at the resting membrane potential, or V sub M, and that's when we're at about minus 70 millivolts. They only open and let ions flow through when they get to a certain threshold voltage, And the threshold voltage is going to be at negative 50 millivolts. So these will open at a threshold of negative 50 millivolts. So the cell is normally at negative 70 millivolts. There's going to be some sort of stimuli that causes it to depolarize just a little bit to negative 50. If it reaches negative 50, both of these voltage gated ion channels will open. They'll open with different kinetics, and we'll look at that in a second. But the key here is that if the membrane potential goes from minus 70 millivolts to minus 60, nothing happens. If it goes from minus 70 to minus 55, nothing happens. Only something will happen if it hits that threshold, and that threshold is negative 50. So both of these voltage-gated ion channels will open up. Okay, so they're going to open, but with different kinetics. So, and then they're going to close with different kinetics as well. And so let's see how this works. So if we open channels in a membrane, for the sodium ions, we already saw this. They're going to flow one way. For the potassium ions, they're going to flow the other. They're going to flow in their characteristic ways. And we want to know what happens at that one point on the membrane, kind of a little tiny piece of the axon, right? So we're back and looking at a neuron. We define the cell body, the dendrites, the nerve terminus. This red arrow indicates the way that the action potential is going to flow from the cell body to the nerve terminus. And what we're looking at is a really, really small part within that axon, perhaps just this little yellow region here. And so we want to know what's going on here. So the ions have very different equilibrium potentials. We saw that. So things are going in different directions when one channel opens up versus when another channel opens up. The basic thing is that sodium channel opens faster and the potassium will open up slower. So the first will be the voltage gated sodium channel. It'll open and close, followed by the second channel, voltage gated channel, the potassium channel. So we're going to draw a couple graphs, no surprise. The first one we're going to look at, we're going to be evaluating permeability of the ions. So permeability on the y-axis over time on the x-axis. So I define time as 0, 1, and 2. We're not talking hours, minutes, or even seconds. This is going to be really quick in milliseconds. Okay, let's assume that at time 0 here, we had some depolarization stimulus. Something hit that area of the axon that we just looked at. It caused the membrane potential to become depolarized from negative 70 to negative 50. And the first ion that's going to be able to permeabilize the membrane is sodium. And that's because the sodium channels, voltage-gated sodium channels, open first and then they close. And so this is going to be what permeability of sodium ions look like. Remember that they're going to be entering into the cell. So because the channels open up, the membrane is going to be permeable to them, of course, not through the lipids, but through the channel. Nonetheless, the membrane's permeable. It's selectively permeable. It's letting sodium ions enter in. And then at the peak of this, the sodium, voltage-gated sodium channel closes and that permeability ceases. And we'll see that the potassium, voltage-gated potassium channel opens a little bit later and then closes a little bit later. So looking at permeability of potassium ions through the membrane, As this line goes up, that permeability increases, meaning potassium ions are able to flow towards their electrochemical gradient, which is in this case outside of the cell, and then that channel closes a little bit more slowly. So it's the difference in behaviors, really just the intrinsic behavior of these two ion channels. Okay, so in that first millisecond, the membrane potential is going to get a little bit more positive. Why is that? Because sodium's flowing in. As sodium channels close and potassium channels open, potassium flows out and the membrane potential is going to get a little bit more negative. Now there's some links in your lecture notes with videos. The publisher's videos simplify it too much, so take a look at the links in the lecture notes that I provided to you. And you'll also see a schematic that looks like this. That's right out of your textbook that looks very similar to what we just drew. All right, but there's another way to represent this in a way that is actually quite a bit better for us to visualize. We're still going to be looking at time on the x-axis, but on the y-axis, we'll be taking a look at voltage. And the volts are going to be in millivolts. We'll start with 0, and we're going to go up in steps of 20, so 20 or 40 millivolts, and then we're going to go down in steps of 20, negative 20, negative 40, negative 60, we'll get down to negative 80 millivolts. And on the x-axis, we're still dealing with time, 0, 1, and 2 milliseconds. Now recall resting membrane potential is at minus 70 millivolts, so I'm going to start a line here at minus 70 millivolts, because that's where resting membrane potential is. Now let's assume that we had our initial stimulus. That does what? It's going to depolarize the membrane. It'll depolarize it to negative 60. Nothing happens, but once it hits negative 50, and just to be clear here, negative 50 millivolts. Once it reaches that, what happens? The sodium channels open. When the sodium channels open, sodium permeabilizes through the membrane and it allows sodium to enter. Sodium is a positively charged ion, so when it enters, the voltage of the membrane is going to go up, and in fact it's going to be hyperpolarized to a positive state. And so again, following with the colors from the previous one, that's the sodium ion that are entering or coming in. That's resulting in this hyperpolarization. Okay, now at about that time, the sodium ions start to close and the potassium ions open. Potassium's moving in the opposite direction, so all those positively charged ions are going to be leaving the cell, and that's going to result in the membrane potential dropping back down, and it actually drops down below the resting membrane potential, because you'll recall that the equilibrium potential of potassium is negative 90. So it actually approaches the equilibrium potential. So this is for potassium, and it's flowing out of the cell. All right, so then there's one more situation that I want to talk about. It's this kind of lowest peak down here that results in really the lowest voltage in this case. We refer to that as a refractory period, and it's going to be restored to negative 70 millivolts by another channel. It's another leak channel, but it's a chloride leak channel. And chloride's a negatively charged ion, so just by looking at this, if we're going from, let's say, negative 90 to negative 70, we're becoming more positive. So you can make kind of an observation that calcium would be going out of the cell through this leak channel to restore the resting membrane potential to minus 70 millivolts. Okay, so this is kind of the action potential, but it's all happening at one particular point. And here's the diagram straight out of your textbook. But the question we have is, how does this event and the properties of the membrane that you understand result in a very rapid depolarization, moving along the axon at 50, 75, and even 100 meters per second? So to understand that, I want to now consider propagation of the signal. So there's a pretty useful cartoon that I'll pull up for a second, and then we're going to kind of recreate it on the OneNote side. So what we're looking at in this cartoon is the axon in the center, that would be the cytoplasm is, and then on the top and the bottom are plasma membranes, and we're looking at different charges. And I'll reference back to this in a second, but let's go ahead and recreate this. So I'm going to draw the two lipid bilayers, the axon here. So this would be inside the cell, and then up here and below are both outside. And so we're somewhere along an axon, which continues on in both directions. So a couple things to think about. Let's say we just had an action potential right around in this region. Okay. Remembering that, where were we? We were at a negative charge inside both leaflets, meaning that outside the cell we had a more positive environment. And if we just had an action potential, we would have had two different voltage-gated ion channels that were involved. So I'm just drawing them as these blue and green boxes to indicate sodium, voltage-gated sodium channel, and in blue, the voltage-gated potassium channel. Now I'm just drawing them on one side. They would be on both sides of the cytoplasm, but we'll just follow it on one side. So if you just had an action potential that just happened, so what would happen would be you would have some level of depolarization in that region. So this would become, at some point during that action potential, actually hyperpolarized, where now you have positive charge on the inside. And when did that happen? That happened, go up for a second, when the sodium ions were being let in and they were at essentially their peak. So in this case, at about positive 40 millivolts on the inside. All right, so we had this depolarization because those two channels opened and closed, and sodium opened first and allowed the ions to come in. So in a little region during the action potential, we have something going on, and that's that the charge across the membrane is transiently reversed. So we have this depolarization in this one spot during that action potential, and as a result, we have a positive membrane potential. And as you know, little things like ions can rapidly diffuse, and we call that current flow. So down here, downstream, the membrane would again be negative 70 millivolts. But if there's current flow, some of these positive and negative charges would flow into the region of the other. And so that's really what I'm going to refer to as step number 2, where we have current flow. So that transiently positive region in the yellow is going to pull some of the negative charges out of the region next to it. And so what is that doing? It's slightly depolarizing the adjacent region to the right that I'll highlight in pink. So we're getting a little bit of depolarization there. Now, if you're too far away, you'll have less depolarization, but if you're relatively close, the current flow will depolarize that adjacent region from negative 70 to negative 50. And if it is negative 50, you'll have additional voltage-gated sodium and potassium ion channels in that region that will now be triggered to open And so what you end up having is depolarization of a nearby region. And again, if that depolarized region is close enough to another set of voltage-gated sodium and potassium ion channels, the channels will open. And then the same situation would happen downstream from that. Okay, and so we can go back to the PowerPoint and see how the artist has this indicated here. Again, in yellow is where the action potential occurred. Current flow is shown in red. And then you have that second depolarization to the right in this particular schematic that we're looking at here. So by its nature, we have an action potential. By its nature, the membrane, nature of the ion channels, nature of the stimulus, and just through physics, through current flow, that local depolarization, which is big, will induce a small depolarization downstream, but that's enough for an action potential. And so therefore we have depolarization of a nearby region and so on and so forth. So the action potential is always going to get propagated in one direction. We said that it's unidirectional. Some of you may be asking why it doesn't go in the other direction. What makes it only go in one way is the question we had. It's a really important part of this unidirectionality. And it turns out that the unidirectionality is due to intrinsic properties of these ion channels, in particular the sodium channel. So a property of the sodium channel is that when there is a depolarization and it opens and closes, there's what we refer to as a refractory period. So there's a refractory period only for the voltage gated sodium channels. And this prevents we'll say backwards and I'll just kind of put that in quotes, action potential. So what do we mean by the refractory period? Once it's opened and closed, it can't reopen just for a few seconds. So once the voltage gated sodium channel is open and closed, it cannot reopen. For just a few milliseconds, but it's enough that by the time it can reopen, that depolarized membrane has returned back to the resting membrane potential. So the unidirectionality is due to this. So it's due to that refractory period of the sodium channel. So let's take a look at this in cartoon format from your textbook. Or actually, this is from a slightly better article that I pulled this in. So we have a sodium channel that is closed on the left-hand side. And when we hit a threshold depolarization, they're going to open. We just saw the effects of that. But when they close, they can't reopen again for a few milliseconds. What that means, if we kind of look at the middle one, it's open and we can see the ions flowing through. But on the right-hand side, what the artist has drawn is kind of this little kind of ball that gets stuck in there. So a channel that was just opened, let's say in this region over here, that ultimately generated an action potential towards the right, any channel in that circle can't be reopened for a few milliseconds. By the time it's ready to be reopened, this charge in yellow here has dissipated enough that you will not reach negative 70 or negative 50 millivolts to the left of that yellow box. Only the ones to the right that haven't opened yet can be opened. So the sodium channel has 3 states. It has the state of being opened on, in the middle, closed on the left, inactive on the right. So 3 states. Can be either open, closed, or inactive. All right. So the essential elements for signal propagation that you should be taking away from this lecture are shown on this slide here. So recall that the cell has a resting membrane potential we define as V sub m, but it has different electrochemical status for sodium and potassium ions. Sodium's out of equilibrium in one direction, potassium's out of equilibrium in the other. There are 2 very important voltage-gated ion channels, and they're going to open and close with different characteristics. Sodium opens and closes faster. The potassium voltage-gated ion channel is going to open slowly and then close more slowly. And then it's just physics. Current flow means that a big depolarization in one region is going to be felt in an adjacent region, and we define that as current flow. And if it's far enough downstream that it can induce a subsequent action potential. In vertebrates like us, it's sped up due to insulation provided by myelin sheet coating. And then we have this last point here for the refractory period, means that you don't get feedback because the signal can only go in one direction, and that's due to the 3 states of the voltage-gated sodium channel: open, closed, and then inactive for a short period of time, preventing it from being reopened up. So those are the kind of the end of this lecture that we needed to get through. I will upload a second full lecture thinking about how we're going to look at this quantitatively.